A 246-foot missile carrier is lying on a beach beside the Caspian Sea. 6 anti-ship missile launchers still sit across its back. Its wings look too short, its hull looks too heavy, and the entire machine resembles a warship that somehow missed the ocean. Yet it was built to move at roughly 310 miles per hour, only a few yards above the water. This was the Lund-class Ekranoplan, one of several Soviet machines created after normal engineering categories had been declared inadequate. Engineers pulled aircraft close enough to the sea for the surface to alter the airflow, multiplied wheels beneath strategic missiles, and replaced tires with rotating screws when mud swallowed normal vehicles. Each machine answered a specific physical problem: induced drag, airflow separation, structural vibration, unstable cargo, ground pressure, terrain failure, recoil, or the energy demands of a battlefield laser. Some answers worked. Others revealed a colder rule: solving one engineering problem often creates 3 more. During the Cold War, an American reconnaissance satellite records an object nearly 330 feet long moving across the Caspian Sea. It is far faster than a warship, yet its wings appear too short to support an aircraft of that size. The wake proves it is real. The proportions suggest it should not be airborne. American analysts called it the Caspian Sea Monster. Soviet engineers called it an Ekranoplan, a vehicle designed to operate inside ground effect. A conventional wing creates wingtip vortices. Higher pressure air from beneath the wing curls toward the lower pressure region above it, bending the wake downward and producing induced drag. Close to a surface, that vortex system cannot develop in the same way. Downwash is restricted, induced drag falls, and a broad wing can support a heavy vehicle more efficiently than it could in free flight. NASA testing has documented how ground proximity changes lift, drag, pitching moment, and stability, especially for low aspect ratio wings. The Ekranoplan did not defeat gravity. It reduced one of the largest aerodynamic penalties involved in fighting it, but the benefit existed only inside a narrow altitude band. Rise too high, and the effect weakened. Drop too low, and the water stopped acting like an aerodynamic boundary and became an obstacle approaching at more than 300 miles per hour. Pitch changes were equally dangerous because altering the gap beneath the wing changed both lift and stability. The original Caspian Sea Monster crashed in 1980 after roughly 15 years of testing. The concept continued through Lund, a 246-foot strike platform carrying 6 anti-ship missile launchers that entered service in 1987. Today, tourists stand beneath a machine designed to approach naval groups at aircraft speed. The craft that used the Caspian as part of its flight system is now stranded above it. Ground effect made the surface useful. The VVA-14 tried to make the choice of surface irrelevant. A ballistic missile submarine has disappeared beneath the ocean. The aircraft hunting it must travel quickly, operate close to the waves, survive contact with water, and still climb to conventional altitude. Then another requirement is added: vertical takeoff. The result was Robert Bartini's VVA-14, intended to operate from water, fly in ground effect, and climb to roughly 33,000 feet. The complete concept also called for 12 lift engines. Those engines would have worked only during takeoff and landing, while their mass and supporting systems remained aboard throughout the mission. More systems add weight. More weight demands lift, power, fuel, and stronger structure. The 12 lift engines never arrived. Without them, the VVA-14 could still fly, but one of the main operating modes behind the design no longer existed. The failure was integration. Too many demanding roles had been assigned to one airframe, and the incomplete aircraft could not justify compromises made for equipment it never received. After Bartini died, development ended, and the surviving prototype eventually reached the museum at Monino. But what if the breakthrough did not come from adding more flight modes? What if it came from changing the shape of the aircraft itself? EKIP began with a disk, and a boundary layer problem large enough to threaten the entire concept. A disk can create lift. The difficult part is controlling the air as it reaches the rear. Air touching an aircraft surface is slowed by friction, forming a boundary layer. Farther back, that slower air moves into rising pressure. If it loses too much momentum, it can slow, reverse locally, and separate from the surface. Once separation begins, a broad, turbulent wake forms. Pressure drag rises, and stability suffers. For EKIP, almost the entire aircraft was a thick lifting body. The shape created enormous internal volume, but it also created a wide rear surface where airflow could break away. The proposed solution was active boundary layer suction. Openings in the upper rear surface drew away the slow-moving air most likely to separate. Removing that weak layer allowed faster external air to move closer to the body. Because this replacement air carried more momentum, it was better able to follow the curved surface against the rising pressure. In visual terms, EKIP was trying to vacuum away the air that had become too tired to remain useful. Maximum suction would have wasted power, so the patented concept used vortex chambers, valves, and controlled airflow. The system increased suction until the external flow reattached, then reduced it to the minimum needed to keep the wake under control. EKIP was therefore not simply a saucer with holes and a fan. It was a thick, lifting body that depended on active airflow management to stop its useful internal volume from becoming a giant source of drag. An air cushion landing system was also proposed, spreading the vehicle's weight so it could operate from water, snow, open ground, and other unprepared surfaces. Reduced-scale prototypes demonstrated parts of the idea, but no full-size production aircraft followed. Its greatest promises were never proven at operational scale. The shape looked simple. Keeping the airflow attached required another machine operating inside it. The aircraft is still flying, but its structure is no longer moving as one object. Engines create repeated pulses. Long members bend. Tail structures respond a fraction of a second later. Vibrations travel through the frame and return through metal, carrying alternating stress. To the crew, the aircraft is shaking. To an engineer, it may be approaching one of its natural modes of vibration. The Kalinin K-7 first flew in 1933. Its wingspan exceeded 164 feet, and the wing was thick enough to contain passenger compartments. A proposed military version was expected to carry roughly 44,000 pounds of bombs, or more than 100 paratroopers. The completed aircraft weighed close to 66,000 pounds. Large structures are not perfectly rigid. Their wings bend, their tails twist, and each major section has frequencies at which it naturally prefers to vibrate. If engine or aerodynamic forces arrive close to one of those frequencies, each pulse can reinforce the motion already in progress. That is resonance. Repeated flexing creates cyclic stress. A load too small to break a component once may still damage it after thousands of repetitions. The K-7 suffered serious vibration during testing, and engineers modified the structure in an attempt to control it. During a later flight, the aircraft crashed after failure in the tail area. Historical accounts differ on the exact sequence, but the K-7 had clearly entered a structural regime its designers could not reliably predict. It was not simply too large to fly. It was large enough that different parts of the aircraft could disagree about how to move. Now take that moving mass out of the airframe and hang it nearly 33 feet below the rotor. A prefabricated drilling module is sitting in a remote forest. There is no road wide enough to carry it, and constructing one could consume more time than the industrial project itself. The Mi-10 approaches on 4 towering landing legs and positions its fuselage above the cargo. Those legs created an open loading space beneath the aircraft. The helicopter could lift approximately 33,000 pounds, enough for buses, cabins, tanks, and industrial equipment. Once the load left the ground, helicopter and payload became one dynamic system. If the cargo hung from cables, it behaved like a pendulum. A crosswind could push it sideways, and a poorly timed pilot correction could add energy to the swing instead of removing it. The cargo also had its own aerodynamics. A dense load might hang predictably, while a cabin or vehicle could yaw, pitch, or oscillate in forward flight. The pilot was controlling a helicopter attached to a second moving body with its own momentum and drag. FAA guidance similarly treats rigging, weight, balance, and external load behavior as core operational concerns rather than secondary details. The load path ran from the cargo through the sling, fuselage, rotor mast, and finally the blades, while the flight controls stabilized the combined system. At demonstrations, the Mi-10 carried buses, cabins, and even a staffed pavilion. Several dozen Mi-10s were built, and some worked for decades. Its strange appearance was not a failed experiment. The long legs turned the space beneath the fuselage into a cargo bay without walls. Airlifting 33,000 pounds is one solution. Carrying more than 10 times that amount across land requires a different negotiation, with pavement, axles, steering geometry, and a chassis almost 100 feet long. Begin beneath the tires. A strategic missile and its carrier can place hundreds of thousands of pounds onto the ground. Concentrate too much weight on a few axles, and the machine may damage pavement, overload bridges, or sink into soft terrain. More axles distribute the load across more contact points. The MA-7904 reached approximately 98 feet in length and was designed around a load of roughly 440,000 pounds. A later transporter carried 24 wheels across 12 axles. Road engineering research similarly treats axle type, axle loading, spacing, and vehicle configuration as major factors in pavement stress and design life. At that scale, steering became as difficult as carrying the weight. During a turn, every axle follows a different radius. If the wheels remain parallel, many are dragged sideways across the road. This tire scrub wastes power, damages rubber, and forces lateral stress through the hubs and frame. Multiple axles, therefore, had to steer in coordinated patterns, reducing the conflict between the direction each wheel faced and the path it needed to follow. Then came chassis torsion. A 98-foot vehicle cannot remain flat over uneven ground. One corner rises while another stays low, twisting the frame along its length. Make the chassis too rigid and stress concentrates around joints. Make it too flexible, and the missile support system loses alignment. Separate cabins gave crew members different views around a machine too large to understand from one seat. The largest prototypes never became a full strategic fleet. One surviving 24-wheel machine later transported ship hulls. It could not make the cargo lighter. It could only persuade the ground to accept the weight in smaller portions. That logic works only while the surface beneath the tires remains solid. In deep marshland, even 24 wheels would still be 24 ways to sink. Place 3 vehicles at the edge of a marsh. A wheeled truck enters the mud, loses traction, and digs downward. A tracked vehicle spreads its weight better, but when the soil becomes too weak, its tracks churn the surface into slurry. The ZIL 2901 has neither wheels nor tracks. Along each side sits a hollow cylinder wrapped in a helical ridge. As the cylinders rotate, they push mud, snow, sand, or water backward and sideways. The surrounding material resists that displacement, and the reaction force moves the vehicle forward. The principle is closer to a marine propeller laid on its side than to a normal drivetrain. The helix angle determines how rotation is divided between pushing material sideways and producing forward motion. But mud flows, snow compacts, and sand slips, so part of the rotation becomes deformation instead of useful travel. A geometry that works well in water may sink too deeply in soil or waste energy on firmer ground. Modern screw propulsion research confirms that helix angle affects speed, thrust, slip, sinkage, and efficiency differently across various media. That explains both the brilliance and the limitation of the ZIL. In marshland, broken ice, and snow, the screws had material to push against. On pavement, the steel helices scraped against a surface too rigid to cooperate. The vehicle managed only a little more than 9 miles per hour on land, but machines of this family were associated with recovering cosmonauts beyond reliable roads. A fast rescue truck was worthless if it stopped at the first swamp. The ZIL's achievement was mechanical independence from the existence of a road. Propellant gas expands, and a 1,650-pound projectile accelerates through a barrel nearly 66 feet long. The projectile moves forward. Equal momentum is transferred backward. The shell leaves. The recoil remains. That recoil travels from the breech into the barrel, mounting, frame, suspension, tracks, and finally, the ground. Every connection must carry the load, absorb part of it, or fail. The time over which momentum changes is critical. If a recoil mechanism allows controlled rearward movement, it spreads the impulse over a longer period and reduces peak force. The same reason catching a heavy object while moving your arms backward is easier than stopping it instantly. The Oka's scale pushed that problem toward the limit. Its bore measured approximately 16.5 inches, and it was designed to fire nuclear projectiles across many miles. Reports from testing described damaged running gear and transmission components torn from their mounts. The weapon fired, then demanded repairs for having done so. Loading was slow, concealment was difficult, and every shot punished the chassis. Then compact missiles arrived. A missile carried its propulsion system with it and did not require a tracked chassis to absorb the same artillery recoil through a rigid barrel and breech. The Oka did not lose because it lacked force. It lost because rocketry offered a cleaner place to send it. After building a weapon that punished itself through recoil, Soviet engineers pursued a different form of force, one that carried almost no momentum at all. A laser tank appears simple only in science fiction. Aim, fire, burn through steel. The 1K-17 Shotty pursued a more complicated objective. It aimed to disable the sights, cameras, rangefinders, and sensors that allowed an enemy vehicle to fight. Public details about the classified layout remain limited, but a pulsed ruby laser first requires stored electrical energy to drive intense flash lamps. Chromium ions in the crystal absorb that light, and mirrors send photons repeatedly through the ruby until part of the amplified light exits as a laser pulse. Every conversion wasted energy. Fuel became mechanical rotation. Rotation became electricity. Electricity became broad-spectrum light. Only part of that light became a coherent beam. Much of the remainder became heat. Cooling was therefore part of the weapon. Uneven heating could distort the ruby and degrade the beam, while pulse power hardware had to store energy over time and release it rapidly during firing. Research on flash lamp-pumped lasers confirms that thermal effects can alter the refractive behavior and divergence of the beam. The turret needed power generation, electrical storage, flash lamps, laser cavities, cooling hardware, targeting optics, and alignment systems. Then the beam had to cross the atmosphere. Dust scattered it, fog absorbed it, heated air distorted it. The target optic might be small, moving, filtered, or pointed away. Shoddy replaced the problem of armor penetration with a systems engineering problem involving energy, heat, optics, detection, and tracking. It was not a tank carrying a futuristic cannon. It was a mobile, pulsed laser laboratory wearing armor. The machine did not need to punch through steel. It only needed to make the steel blind. Lun used the C to reduce drag. EKIP removed weak boundary layer air before separation. The K7 exposed the flexibility of large structures. MAZ spread weight across an empire of axles. ZIL manufactured thrust from marshland. OK absorbed its own violence, and Shati attacked vision instead of armor. Most disappeared because the complete system was too expensive, too complex, or too early. The machines vanished, the equations did not. So which deserves more respect, the machine that worked within the limits of its time, or the machine whose central idea is still waiting for technology to catch up? Subscribe to MegaMass for the next engineering dossier built beyond ordinary limits.